Hey guys, today's problem we're going to be talking about standing waves. And for this we're talking about a bunch of improvised instruments that have been created in order to create different sounds. The first instrument that we're given is a bungee cord that we are told has a linear density of 0.2 kilograms per meter. We are told that it is being held at a tension or a force tension equal to 80,000 newtons, which is a little bit ridiculous, but we're going with it. And we're told that when it's plucked, we want it to be at a length such that the first harmonic, so the frequency at the first harmonic is supposed to be a C sharp, which we're told for this is going to be 277.2 hertz. And this improvised group wants to know a couple things. They want to know what the length of the string needs to be, and they would like to know what the frequency of the second harmonic is going to be for this system. Okay, and then we've got a couple extra instruments, and we will get to those in a second. We're going to go one piece at a time here. So for our first piece, we have this bungee cord, and we have our information on it, and we want to know the length. Well, today we added a bunch of standing wave lengths, and we know that this is waves along a string, where we know that the wavelength is going to be equal to our 2 divided by our harmonic times the length. So we know that is how we're going to end up getting this length, but we need to take a couple steps in order to actually get there. And with what we have, in order to get wavelength, we're going to have to backtrack, and we're going to end up using our wave equation. Our frequency times our wavelength is going to be equal to our velocity for our wave. And then we're going to have to backtrack even further because we do not have this velocity. And that velocity is going to come from our first day when we were talking about sound, and that is going to be the velocity of sound on a string, which is going to be the square root of our force tension divided by our linear density. So that's the generic strategy for what we're about to do. I don't have space to leave all of that up. I might actually, but in this case I'm not going to. So starting with that, we need our velocity in order to get any further here. So our velocity along the string is going to be equal to our square root of our force tension divided by our linear density. And both of these values were just straight up given to us, which was one of our biggest clues that we need to start there. So we've got the square root of 80,000 newtons, 8 kilonewtons, divided by 0.2 kilograms per meter. So they really have this thing stretched pretty taut. And that gives us the velocity of the wave along the string equal to 632.46 meters per second. There is a decimal point in there that I don't think shows up great, but that's our first step. Our second step, we said we're trying to get to length, but before we can get to length, we need to have our wavelength. So our velocity in this case, our velocity along the string is going to be equal to our frequency times our wavelength. So our wavelength for the first harmonic is going to be our frequency for our first harmonic. That times the frequency for first harmonic is going to be equal to our velocity, so our wavelength for our first harmonic is going to be equal to our velocity along the string divided by the frequency of our first harmonic, which is going to be equal to 632.46 meters per second divided by our frequency, which we are given as 277, it's right here, 0.2 hertz. A hertz is a cycle per second, or 1 over seconds. We end up with units of meters, so our wavelength comes out to a value of 2.28 meters. And last step, we still do want this length. So we'll go ahead and take this and we will plug it into our string equation, where we know that the lambda of 1, our wavelength of 1, is going to be equal to 2 divided by whatever harmonic, in this case it's going to be 1, times our length. And with this, we know this is 1, and I can solve for length. So the length of my string is going to be equal to my wavelength divided by 2, which is that 2.28 divided by 2, which is going to be 1.14 meters. So 1.14 meters. And for the record, that length is the distance that I have right here. That is that length. Okay. Simple enough. Now our frequency at our second harmonic is really just going to be the same thing. We know the length now. We know n is 2. We can find wavelength, and then we can go back a step. And we know wavelength. We know the velocity along the string. That's going to stay exactly the same as it was in our first equation. And that should get us there. So I'm going to leave that velocity equation up because we're going to want that number. We're not told anything about the tension or the linear density changing. So that should stay exactly the same. So at this point, what I'm going to do is I'm going to go ahead and write down lambda 2 is going to be equal to 2 divided by n times my length. In this case, my n is 2, so 2 divided by 2 ends up as 1, and my length is 1.14 meters. That should give me an overall value for my wavelength of 1.14 meters. And then in order to find the, we'll go ahead and draw that up quick. So what that is a wave that's going, instead of like that, a wave that's going like so. I'll do both sides of the piece. So that is my second harmonic. And with that, I want the frequency of it. So velocity is going to be equal to our frequency times our wavelength. We have our wavelength. We have our velocity. We want our frequency. So this is going to be our frequency is going to be our velocity along the string divided by our wavelength. And that is 632.46 meters per second. Kept it on the board, perfect. Divided by my wavelength, which is 1.14 meters in this case. And plugging that in, I get a velocity overall, sorry, not velocity, a frequency overall of 554.4 hertz. So that is 554.4 hertz. that is my first instrument. Okay, and for our second piece, we're told that a student has a length of PVC pipe, and it is set up so that they're banging on it and they are creating a sound, and they want to know what length they need such that the second harmonic frequency of the pipe is going to be equal to the first harmonic frequency of the cord, the bungee cord that we have right above right here. And with this, we are told that the velocity for this is approximately our default velocity for sound in air, which is 346 meters per second. So 346 meters per second is our velocity, and racing this stuff here, what I want to find at this point is again going to be this length, and I'll put it the length of the pipe. And that is what I'm looking for from this one. So I'm looking for this length right here. Okay. With this, we have our pipe, and we can do a little bit of work here. So we know that our frequency 2 is going to be equal to our frequency 1 of our cord, and I know that that number is written right up above here, which is going to be 277.2 hertz. Should probably stand out of the way there. So 277.2 hertz. So I need to set it up such that frequency 2 is 277.2 hertz in this case. And what I can do here is I can actually say that in this case, since I'm talking about my pipe, I can say frequency 2 is going to be equal to, or we'll put it in general terms here. You can say frequency of nth harmonic is going to be the harmonic times the first frequency of that. Where this is coming from is my, how do I want to put this? Lambda n is equal to 2 divided by n times my length of my pipe. So if I have lambda 1, that's going to be equal to 2L. If I have lambda 2, that's going to be equal to just straight L. If I have lambda 3, wavelength 3 is going to be 1/2 L, and so on and so forth. So with this, what we're going to do, sorry, that's not 1/2 L. That's going to be 2/3 L. Sorry, something didn't look right there. We also know that velocity is frequency times wavelength. And we know that the velocity is the same for both of them. So if the velocity 1 is equal to frequency 1 times lambda 1, and velocity 2 is frequency 2 times lambda 2, then velocity 1 and 2 are the same. I can say that these two values are equal. So what I can do with this is I can say that lambda 1 is equal to 2 over L, and I'm actually going to change this. This can be any n. So I can say frequency n times lambda n, and frequency 1 stays frequency 1. Lambda 1 is just going to be 2L is equal to frequency n, which we're going to keep the same, and times lambda n. Lambda n is 2 over n times L. I'm going to go ahead and divide both sides by 2L. So I get frequency 1 is equal to 1 over n frequency n, and therefore frequency n is equal to n times frequency 1. So that's where that equation is coming from, in case we didn't get a chance to discuss that in class. But with that, I can figure out what my frequency 1 is for this system so that I can solve for that L, or I can do it directly, but we're going to go ahead and do it this way. My frequency 1 is going to be equal to my frequency, in this case I have my frequency 2 divided by my n, which in this case is 2. So frequency 2 is 277.2 hertz divided by 2 is going to give me a value of 138.6 hertz. Okay. Moving forward with that, we still want this L. So the first thing I'm going to need to do is I'm going to need to get my velocity. I'm going to need to get my wavelength. So velocity is going to be my frequency times my wavelength. So lambda 1 times frequency 1 is velocity. I can go ahead and say that my lambda 1 is going to be equal to my velocity divided by my frequency 1. And that is going to be equal to 346, which I was given as my velocity of my sound in air, divided by my frequency of 138.6 hertz. And that gives me a wavelength of 2.5 meters. And then with that wavelength, I can go ahead and say lambda 1 is going to be equal to 2 divided by n times L. Same thing we've been doing. And in this case, it's 1, so my L, this n becomes 1. So my L is going to be equal to 1/2 times my lambda 1, which is 1/2 of 2.5 meters, which is 1.25 meters. So the length of my pipe needs to be 1.25 meters. And I'm done. Now this isn't the best way to solve this necessarily. I just wanted to show this guy off. What I could have done straight from the start is I could have skipped this entire step and I could have put this guy in and solved for, I know my frequency 2 and my lambda 2. So I could say lambda 2 is going to be equal to frequency 2, velocity divided by frequency 2. I know my velocity is going to be equal to 346 meters per second. I know my frequency 2 is going to be equal to 277.2 hertz, or 1/2. That is going to give me a value of 1.25 meters for my lambda 2. And then I can go ahead and plug in here. Lambda 2 is going to be 2 over n. In this case, n is 2. So these two 2 cancel. Lambda 2 is equal to my length. My length is going to be equal to 1.25 meters. So that is the easy way to solve it, but just showing off something else we can do. I think a lot of times it's instinct to go ahead and switch it to that first harmonic, that primary harmonic. Okay, so that is our second instrument. On to the third. For my last instrument, I have a graduated cylinder, and that graduated cylinder we're blowing across the top in order to create a sound. And what that's going to do is we've got a 1 meter tall graduated cylinder, and we're told that it's blowing across, creating a sound. First harmonic of that piece is going to be there. However, we want to change this piece such that it shows up as a harmonic of these other two pieces. And how we're going to change it is we're basically going to fill it with water to a certain height. So we've got some height of water there. And we'll call that water. And that is going to create a new frequency, because what I've done is I've gone ahead and I have changed my effective length. So I now have this as my length instead of 1 meter. And I've created a new frequency for it because my quarter wavelength that this represents is getting smaller. So what I want to know is I want to know the height of water. So how much water do I need to add in order to create some harmonic of this 277.2 set of systems here? Okay, so first thing we're going to do is let's go ahead and just see what our frequency is if we've got no water in it, because if that works, then problem solved, we're done. So with that, we know that our wavelength at 1 is simply going to be equal to 4 divided by n, or in this case n is 1, times our length. Okay? And our length is 1 meter, and our n is 1, so 4 divided by 1 times 1 meter is simply a 4 meter long wavelength. And to get frequency from that, we've got velocity is equal to frequency times wavelength. And by velocity, I'm still going through air, and I still have a value for what my velocity is in air. So I can go ahead and say that my frequency is going to be equal to my velocity divided by that wavelength. So I have a velocity of 346 meters per second. I have a wavelength right up here of 4 meters. That is going to give me a frequency currently of 86.5 hertz. Okay, 86.5 hertz. How are we going to work with that? So this number is not this number. That's easy enough to see. And if we divide 277.2 divided by 86.5, we're not going to get a whole number. We're not going to have it already being harmonic. We need to add some amount of water. And how we're going to determine that amount of water, let's go ahead and do a little bit of logic on this. From this equation here, we know that as this L gets smaller, so we're adding water, so L, as we add water, is getting smaller, and that is going to cause my wavelength to get smaller, right? Now, in this case, if my wavelength is getting smaller, my frequency, because I'm dividing by the wavelength, is getting larger. So I need a value, a frequency that is greater. Frequency we require has got to be greater than 86.5 in order for this to work, because we can't remove water. We already have no water in the graduated cylinder. We can only add water. So what I'm going to do here is I'm going to quickly go through and I'm going to check what my different options are that are going to fall under this harmonics of the 277.2. So I will say Fn is going to be equal to n frequency 1, that piece that we just talked about in the previous question. And in the case where I want F2, oops, yep, 1 second. Fn is 277. So I've got 277 because I want some frequency that falls at some harmonic of 277.2 hertz is going to be equal to, well, is going to be related to n F1. And that F1 is that natural frequency that we want to set this at instead of 86.5. So if n is equal to 2, F1 is going to be equal to 277.2 hertz divided by 2. That gives me a value of 138.6 hertz. That is greater than 86.5, so that one would work, as would 277. If we wanted to use n equals 1 and we wanted to use 277, that would work, but we'd have to add more water. So we want to add the least amount of water as possible. So let's check n equals 3. In that case, F1 is going to be equal to 277.2 hertz divided by 3, which is going to come out to, I don't have that number on me. Do I have it in here? 46.2 hertz. My apologies. Okay, well, 46.2 hertz is not greater than my required 86.5. So 138 is the best I can do. So I want to create it such that this F1 required, I'll go back to white here, is going to be equal to 138.6 hertz. And that number is my second harmonic of my overall system here. Okay, so I know what my goal is. And now basically what I'm going to do is I am going to figure out what this height now has to be. So I figured out if that height is 1, it ends up at 86.5. I don't want 86.5. 86.5 is not a harmonic of 277.2. I want it to be 138.6 instead. What does that length have to be in order for that to be true? And for that, what I'm going to do is I'm going to say that, well, I'm really just going to go back up the steps I did before. I'm going to say that my velocity is going to be my frequency 1 times my wavelength. And in this case, I'm not solving for frequency, I'm solving for wavelength. So my wavelength 1 is going to be equal to my frequency 1, which was 138.6 hertz, divided by, sorry, other way around. My velocity, 346 meters per second, divided by 138.6 hertz. And that gives me a value of 2.50 meters. Okay, don't worry yet, 2.5 meters is the length of one wavelength. We only need a quarter wavelength based off of this. So my wavelength is going to be equal to 4 over n times L. And this is my first harmonic. So that n I've already chosen as 1. So in this case, my L is going to be equal to 2.50 meters divided by 4, which will give me a value of 0.38 meters. Sorry. That will give me a value of 0.68 meters. And that is that L. So I want the height of water. So I want 1 minus that L. 1 minus 0.68 is going to give me that 0.32 that I started writing down a second ago. That 0.32 is the height of water that I need in order to set that there. Okay, so that is our value. However, there's something a little bit cheesy about this. So if we actually think about this, what sounds is this going to produce? So we've got, I should probably leave that 138.6 hertz. That is producing a sound of 138.6 hertz. Now, if I go through and I start writing this down, frequency 1 is 138.6 hertz. That is my first harmonic of this sound. Frequency 2, that is going to end up being 2 times that, which is that 277.2 hertz that we talked about. That's what we're comparing it to here. And then frequency 3 is going to be equal to 415.8 hertz. So yes, we're seeing that 277.2 there, except we're not. Because if we think about this, this system, if you recall, only creates odd harmonics. So it creates frequency 1, and it'll create frequency 3, but it will not create this 277.2 sound. So even though we chose that based off the 277.2 sound, and these sounds will share a lot in common, the second harmonic of this system, my pen is dying there, let's grab a different color. Second harmonic of my system is actually my third harmonic. Second sound produced is 415.8 hertz. And interestingly, this is actually a G sharp, not a C sharp anymore, like my original note. Well, that's our problem. Hopefully that was helpful. See you next time.